Hello out there. This is Brian Clark at Searle. I'm here with Chris Battisti and Irene Ansiger. I'm saying that right?
Yeah.
Okay, great.
I would hope by now.
I don't use her last name a whole lot, believe it or not, so it doesn't come up much. Okay, so we'll go ahead and get started. Hopefully everybody saw the slides that we sent out in the last hour. But if not, we'll go ahead and share it on the screen here in WebEx. So we're gonna look at 3 projects today, give feedback, and then we'll rotate for next month. So I'd like to pass it off as soon as I can to Redstone. I'll go over a few kind of housekeeping items, but Mark, Patrick, are you guys on the line?
We're here.
Okay, great. I'll show your system diagrams on my side, but if you want to share anything from your inventory or pick list, just once we get started, let me know.
Okay.
All right. Well, I think we had a lot of successful team calls in the past week to try to get to this point, and it's been really great to see where people are in their projects. So I'm just going to go over really quickly about where we're hoping to be for next month. So today we're going to kind of briefly talk about that next session, which is kind of we call it the Rcx Assessment Session for next month, but it's really just generating a list of items to be prioritized and to have a monitoring plan built off, trying to wrap our heads around what all the opportunities are so we can pare down from there. But really the whole call I'm hoping today is going to be on a deep dive on these 3 projects. So this is kind of a newer thought we had to model it in this way rather than have a short amount of time on more projects to allow enough time to really go deeper and give some of that deeper technical feedback. So that was the point of the team calls, and that's how we have the structure here. But if there's any feedback that any of you have after doing this today about a different way to do it, or always if you have some kind of side questions about specific issues, you can send them to us, and we can try to get the group involved. But today we're just gonna, for the 3 projects, try to give a quick refresher on the facility basics, what type of facility it is, when it was built, what control system's in there, how it benchmarks. We're gonna, instead of have the project folks present their system diagrams, we're gonna ask others on the call if they can figure out or what they think about how things are configured, controlled, balanced, based on what we got on the screen. But definitely make sure, like Mark and Patrick, once we get started, if we're getting close to the 30-minute mark and there's really specific stuff you want to get feedback on that we haven't touched on yet, we want to make sure we do that. And then, the goal is to be able to give some next steps for going back into the field next month and generating that list, that findings list. So the emphasis is going to be on based on the facility type, based on the utility data you may or may not have, and based on these system configurations and what you saw in the field, what are going to be the things to check for. Okay, so this is the agenda for what we plan to look at today, and we're hoping to squeeze this into the next hour and a half. So just a kind of quick recap of where we're at right now. So the goal is that we all have this stuff submitted, the system diagram for this month, and the equipment inventory we didn't ask to collect, but if you have some kind of inventory, at least for the systems you're looking at, having that product data is going to be helpful, I think, as you take a deeper look at the system. And if you have it for us, then we can help you look at some of the features or some of the data that you might have to look up. And then the pick sheets. I know a lot of you had submitted in this format, which is really helpful for us and is going to be helpful on these calls. So as you continue with the projects this year, I would just encourage you you'll probably find things to make changes in the system diagram. You might add inventory items, and definitely add any pictures for things that you continue to look at in the field and update that on MillSuite. Okay, and for next month, the goal is to have some of these Rcx assessment sheets completed. So let me just kind of step into this view. So this is a findings checklist that we've made that we found is kind of helpful, just to put a lot of the opportunities kind of categorized together for different common systems that you find out there. So what we're planning on doing is the highlighted bits here for a project we've used in the past, we're going to try to help you get to that point. So before you go back out to the field, you'll have some highlighted stuff that you'll know to look out for. And then you can, in the field, decide which of these apply and which ones might be some pressing priorities. The issues and resolutions log, which there's also a template on this on the Mill Suite site. This is more of an internal document that if you find something that you want to fix on the spot, it's not going to be worth calculating. It's just a quick scheduling fix or some insulation fix or something that you put a work order in to get fixed right away. Like Irene and Chris had pointed out on their building at Leavenworth how there was the pot feed ball valves that were open. That's the kind of thing that I can't imagine that, David, you might have an anecdote out there, but I know when we found these things, we would usually just fix them on the spot. So you still want to document it, but it doesn't need to be part of the greater findings list. So that's what this document is really meant to do, is be a blank register of all the stuff that you find in the next month and that you may add to. And we'll have a final RCX measures list by the end of it that'll have calculated numbers and implementation recommendations. This is just the kind of first step where you're going to be putting stuff in that's going to be this type of generality, where you're seeing that there's multiple outside air sources for your one specific airside unit. That seems like an opportunity to try to optimize and get the right one, and you don't know what is going to be on the table for that yet. You just know that that's a finding, that there's a potential issue there, and it is something you want to look at more. So this is the deliverable for next month, is having some initial submission for this document on Mill Suite. And I'll just pause there. Is there any questions on that for what the goal is for next month?
Brian?
Yeah.
There it is. My only caveat is on the quick repair thing is if you're in a program of some sort, you got to baseline it. Otherwise, you'll get the savings, but you lose the incentive. So. Yeah,
very, very good point. So if there's some retro commissioning, utility funded program where you need to capture that baseline, even little things like a scheduling change is an easy fix, but it might have big repercussions that you may lose out on some kind of rebate. So yeah, thank you, David. It's a good point. And with that, if there's no other questions, I'd like to turn it over to Mark and Patrick. Do you guys want to give? I've just got 2 slides here on your facility profile and your utility data. Do you want to just take a brief 2 or 3 minutes to kind of refresh us on what the building is you're looking at, how it benchmarks, and what kind of systems we're going to be looking at?
Sure, yeah. Just to cover that real quick, it's just about a 35,000 square foot admin type facility. It's several private offices and a few, I guess, medium-sized cube farms type space. It was originally two buildings. They were about a little over 12,000 square foot apiece, and then they built a connector when they renovated and made it into one really long building. So it's got 2 chill water systems with air-cooled chillers, one north, one south. It's got one hot water reheat system that serves the entire building, and it's VAV reheat. The air handlers are cooling only. We did a site visit yesterday and found out it's a plenum return. They don't have ducted returns, so that may be a little bit of a challenge. As far as the meter baseline goes, we had one of the meters we found out was giving us some faulty readings. So we got that fixed. So this baseline may change a little bit when we pull another one. We got probably about 2 weeks, 3 weeks of data on that so far. So it may look a little different, but I'm assuming it'll be probably about the same. Nothing else, no schedules will change or anything. So.
Okay, great. Yeah, we got that data. If we want to compare since the meter change, anything we can kind of help take a look at that, or that may be something that Ryan may be interested in helping with. But I guess to start with, we thought the chill water might be an interesting one to start with. So I grabbed this from your pick list just to kind of really get a visual on how long and skinny this building is. That is it's a new one on me. So you said you got a chill water, air-cooled chill water system or loop on the north side and then one on the south side. So we're going to look at these two system diagrams and kind of ask some of those questions about how it's configured and how it could be balanced or controlled and what's different between the two mechanical rooms. So I'm actually going to open it up. I think a good way to start may be to kind of take turns as teams and provide some feedback here. And the way I think we can do that is by asking some of those basic questions. So I'll start with the Leavenworth folks. So team one, if you guys are sitting in the conference room there, why don't you take a minute, look at this, and see if you can just answer the first question of how is it configured. So what would you call this chill water system? What kind of system is this?
Okay. I'm assuming you're looking for primary, secondary, or primary. Is that?
Yeah, I think that'd be primary only, primary, secondary, constant volume, variable volume, air-cooled, water-cooled. Yeah, just looking at this, I know Mark gave us some description of the systems, but looking at the diagram, I guess that'd be the first question is, what does it look like to you? And I can zoom in if it's not for any of this stuff. If you guys are watching on the WebEx, let me know.
This is Clinton here. I don't know. I think it looks like to me it looks like air cooled, primary loop, maybe constant volume. I'm not too sure on that one.
Well, this is Jay. It's got a VFD on the pump. It looks like.
Yeah, you're right.
Primary only, or primary system, but
Yeah.
what would control the pump speed?
Yeah, so an interesting question maybe for David for this system. So it sounds like so was the consensus primary only, constant volume?
Maybe the potential for variable flow if the VFDs are on the pumps, but just not sure what would modulate that.
So maybe
You
a
want me to
question.
chime in?
Yeah.
This could be one of those ones where the VFD is actually a penalty, not an asset. My read on it, based on it's one load with a three-way valve, that implies constant flow, and there isn't anything out visible, at least on the system, that would vary the flow intentionally. There is something about the three-way valve that could cause flow variation. Does anybody recognize what that might be? Think about like if I'm a water molecule coming through that strainer and heading towards that cooling coil, and my choices are either go through the cooling coil or go around it. How many people have really looked at what a cooling coil looks like if you really looked at the circuiting and stuff like that? And I guess maybe a different way of asking that would be to ask Brian, there be any value in me showing some pictures of cooling coils or a model of a cooling coil and what that's like?
I think if you had a resource like that we could make available on MillSuite, I think that might be helpful. But I think I know where you're going, and it speaks to the question of how is the system balanced and how would it operate, based on balancing infrastructure that could or couldn't be there. So maybe what I would ask, because I think Leavenworth, I think Presidio just stole your thunder there on that last question. So we'll ask you guys how would you balance this system as it's shown? And I think that might feed into David's your point. Then you can elaborate maybe a little bit.
Sure.
So Brett, for you guys, what's the, yeah, what's there or isn't there that would help balance the system?
Yeah. Is there, Robbie's question was, is there a circuit setter on the three-way valve bypass anywhere?
Yeah, so that's a great question that we were talking to Mark and Patrick about, that I think, David, you're alluding to, that would need to be there to help balance the system and prevent some of that flow variation because of the coil pressure
Right.
drop.
Yeah, so that's an opportunity because at part load you'd save pump energy, but you wouldn't need the VFDs to do it. In other words, if it's a constant flow system and there's no loads that are going to vary the flow, the VFD doesn't have anything to do, and it's actually a 3 or 4 or 5% loss in the food chain to the chiller. Now, if the chiller design could actually tolerate some flow variation, you could consider modifying the system in a way that would let the flow vary to some minimum level and then maintain a minimum flow rate through the chiller somehow. That would add a lot of complexity to what appears to be a fairly small system. And so it's one of those things where on paper you might be able to say, oh yeah, we could save some energy by giving those VFDs something to do. But what it would take to do it would be complex and probably expensive, and then the persistence of that might be marginal. And so you actually, I've done this every once in a while, you might actually save energy by taking the VFD out, which gets rid of a loss, and using it someplace where the VFD can actually do something meaningful for you. So I'll stop there unless Brian wants me to elaborate some more.
No, I think that's great. So that's a finding list item, is to watch and to, I guess, verify, Mark and Patrick, what you had said, that there doesn't appear to be a balancing valve on the bypass, and then
Yeah, that's correct.
okay, and then maybe putting a flag for that could be a test to measure that pressure drop across the coil, since you show the Pete ports there, and you could use the manufacturer's data to actually see how some of that flow variation as compared to the rest of the system. Okay, I also wanted to show, I think it's interesting how different these two mechanical rooms are. So unless there's anything else specific on this, on this north mechanical room, I was going to ask the Presidio folks, if you look at slide 11 and 12, and I'll kind of flip back and forth between these two, it's kind of the way that Redstone described it is they're kind of mirror image. One serves the top half, one serves the bottom half. But what's a few things you can see different between these two chill water systems? So this is the south side on slide 12. And this is the north side we were just looking at on slide 11.
I'm going to pull up the two slides next to each other.
Sure, and this, I don't know if this is big enough, but we kind of have that here.
Well, we got two monitors here, so we'll just do it that way.
Okay, I mean, you don't have to brag about your two monitors, but that's cool. Yeah, so there's a few things, and some of them might be kind of quirks, but some of them seem more important given how the system's configured, and maybe a little bit about the relative size for single load.
Yeah, well, it's hard to tell the pumps on the one on the left.
Yeah. So the one, so it looks like there's a separate pump, and it's on slab in the mechanical room versus what it seems like the system diagram on the left is saying, that it's packaged with this air-cooled chiller. So that's one. I don't know if that's worth a diversion there, but I don't know, David, if you have any recommendations for system diagrams where you have pumps packaged inside equipment, if there's a good way to show that.
Yeah, that was one of my comments I was going to make at some point, that I'd show all the internal piping and pumps. You can just draw a dotted line around it, and say this is the chiller, inside this dotted line. And then, because, for instance, on this pump here, we got a triple duty valve, and if that happened to be throttled, that's a savings opportunity that you would not really see on the other system diagram. Plus, on a more complex package with multiple evaporators and stuff like that, there may be some things of interest. Like, didn't the other one, I'm backing up here, I think the other one it has two pumps. So, are they redundant, or do you have to run them both? And if they are redundant and they are running them both, that may be an opportunity there. So I think capturing that's important, bottom line.
Okay. And there's one other.
And the triple duty valve on the south one?
Yeah, absolutely. So just having a infrastructure to help with the balancing, and maybe potentially something to measure across, or help with some pump optimization. There's one bigger one, or to me at least, is really noteworthy. It's different between the two.
Well, one has sensors and the other doesn't. One has sensors that's not connected.
Yeah, so there's still question about how it could be controlled, and I guess ensuring that those sensors that are not connected aren't still driving something, and understanding what's running the chiller and the pumps and the coil valve. But from just a configuration and infrastructure change between the two, do you guys see anything else at Leavenworth between the two that kind of affects a relatively small chill water loop like this with a single load?
We had somebody ask questions of what the little red right before the triple duty valve and then right after the air separator, what those little symbols were.
I think those are, it's not really zoomed in. If it was zoomed in, I think it'd be clear, but I think those are manual temperature gauges.
Oh, okay.
So I think I'll point out what I thought was interesting, and maybe David, you could elaborate, or Mark, Patrick, if you know more about the design intent here. But they seem like they're supposed to be more or less identical mirror images, but this one's got a 52-ton chiller with thermal storage of some size. But on the south side, they've got a bigger chiller, 60-ton, and no thermal storage. So I know, David, you've had a lot of experience with flywheel cycles and the implications of not having enough thermal storage and what that could do to your chiller. Do you got any suggestions for the Redstone folks based on that for the south side?
Yeah, that's a really good observation. Because one of the issues that can come up with a small system is you can't unload far enough. And so you do start short cycling compressors, even on a chilled water system. There's a tendency to think that a chilled water system itself, solves the short cycling problem, but if it's a small system, it won't. And that Lacan Annex example I talk about a lot is a pretty good illustration of that. Some of the things that ripple out, at least in my head, if I was just thinking about this, it could be somebody recognized that, and the 60-ton chiller has hot gas bypass on it, which is what keeps it from short cycling, but that's also an energy intensive thing, which means you may actually be able to justify making a modification like a buffer tank or just implementing a flywheel cycle to get rid of the hot gas. And in fact, I'd actually look for hot gas on both of them because they're small systems with low thermal flywheel potential, and somebody could have recognized that. if there is hot gas there, I'd log it to see if it's working, because it's usually a pretty big opportunity. Another thing that's kind of related to this, the tonnages are the same. It's like, even though they're mirror images, there are two different designers or something, because like one has a package with 2 pumps and the other one has a chiller with 1 pump. And the raw, basically horsepower per ton on the pumps is a little different, and that could be telling you something too. It could be the 2 5 horsepower pumps are only loaded to a total of 7.5 brake horsepower. But it's just something that I'd be getting curious about. Like, they aren't exactly similar systems, so they may merit their own closer attention.
Hey, David, this is Mark at Redstone. That 60-ton chiller on the south mechanical room, this building was renovated, and when the middle section was combined with the two adjoining buildings, the south mechanical room chiller was an existing chiller at the time. I believe the north mechanical room chiller, the air-cooled chiller, was new when the renovation was done.
Mm-hmm.
So in our thriftiness to save money and equipment replacement costs, that's why the chillers are different.
Yeah, and so, and there's nothing wrong with that. I'm thinking, all I'm really saying is, I think when I first looked at this, and at some point somebody said they're mirror images of each other, I was expecting them to be like identical, and they aren't. And so that changed how I was looking at it. That's all. That's all.
Okay, so I'm gonna move. So there's some really interesting stuff going on with the hot water system. So unless Mark or Patrick, you guys wanted to ask anything specific on the chill water, and we'll follow up and kind of help highlight what we think based on this call, or some of those kind of next steps on the next walkthrough. But there's some interesting configurations here on the hot water system. So we're trying to think of the right way to kind of frame this to the class, but one of the things we were working with Redstone to do is to kind of take this, which they did a really good job untangling the system, and they added in the load equipment on the zone side, the VAV reheat. And I think you can tell, like, I'll just ask, so Leavenworth, do you think this one is a primary only or primary secondary?
The tentative answer we got was a variable primary secondary system.
Okay. Yeah, and it's so this I thought this was a really good point worth pausing on, is that we talked about last month how the system diagrams can be really iterative, and this is so this is at the untangled stage, and then we worked with Redstone to get it to this stage, which we think is the same system, but it's kind of organized into more of a to kind of represent that primary secondary configuration, and organize them a little bit more on having the load management equipment on one side, zone level on the other side, low pressure on the bottom, higher pressure on the top, with the bypass really clear. So I hope in doing this, Patrick and Mark, we didn't violate anything that you wanted to show that's important. So we definitely want to make sure to circle back and I mean, Irene and Chris and I were sitting yesterday kind of mapping this out, which was a fun exercise. We all seem to get the same answer, but I think this is the system. I think this is the same system, just reorganized in that way. So I guess
that final version was my full intentions to begin with, but you helped me get there.
Team effort. Yeah. So what do you guys think about this? Is it and I guess maybe open up to everybody. Is it clear that it's a primary secondary system, and do you see anything worth talking about on the configuration of this?
Question we ask here is, why is there 2 bypasses?
Yeah, that's a very good question. Does anybody feel like they've seen a system like this that they want to add add an answer or a guess as to what purpose that serves?
Is this a VAV system?
Yes.
Yeah, VAV. Okay, because this reminds me of Building 52 boiler system. Because we have bypass in there, kind of like on your first slide. And then we have the main pumps for the building, so it's kind of like it modulates for all the VAVs for the hot water coils.
So is it that one of those is acting as a neutral bridge and the other's acting as the flow control?
Is that Zach?
Yep.
Yeah, no, I think you're onto something there. That it looks like one, and we could pull up the piping pictures that you guys took at Redstone, and it does look like there's the bypass, the decoupler as we show it, the straight line going up and down. That is for that neutral, hydraulic decoupling. And you would think that the modulating valve then does flow control. What would be the purpose of that flow control? Why would you need that? Or why do you think a designer might think that you need that? And Zach, I'll just, if you want to keep going on that thought. Sorry, Zach, I think I cut you off. Did you?
No,
Go ahead.
that's okay. I'm sorry, I'm deep in thought. Because they're not getting that control at all of the they're getting that control at most of the VAVs. I'm not sure.
Well, I think one clue might be, and I don't know if that was you, Jay, if you had a thought, but a clue to me is what the Redstone folks put in there about the boiler capacities.
Yeah, can I make a guess here?
Yeah, go ahead.
Seems like the same thing that they were trying to do at 422 on the design on the medical clinic was making sure that we had flow through the boiler at all times at the right GPM, so it didn't burn it up.
Yeah. There's two things I think that the manufacturer may care about let's back up. Is this a condensing or a non-condensing boiler? Or can you tell that from this, which I think is an important thing to note?
Well, you could look at the output-input ratio, right?
Yeah, and I think if you do that math, I think it's somewhere in the 80s. It looks like.
Yeah.
So you guys can correct me, Mark and Patrick, but if this is a non-condensing boiler, in addition to the minimum flow, there might be a concern for maintaining a certain inlet temperature to the boiler so it doesn't condense. And
Yeah, it's a non-condensing boiler,
okay.
and it's about 84%.
So David, I think your input would be real valuable here about if you would suspect the same design intent that we're talking about, and what the concerns would be for a system like this, maybe what that on-off valve could be trying to accomplish.
Yeah, no, I totally agree with your conclusion. That's a very common way of addressing the problem you talked about. In other words, the bypass that doesn't have any valves in it decouples the two loops. And then the three-way valve allows you to keep the boiler loop above the condensing temperature. And if you just think about it from a conservation of mass standpoint, like if the three-way valve opened the port to what its bypass is fully and closed the port to the distribution loop, if you think about what would happen when you ran that boiler pump, it would just pump water around in a circle, right? You wouldn't deliver any heat to the load. So you could warm the boiler loop up that way, and then the control system could basically modulate that three-way valve and start opening the port that connects to the distribution loop, which would let water from that loop come in, and conservation of mass says, well, if water came in from that loop, then water's going to have to leave the boiler loop to get to the distribution loop, and now you start moving heat to the distribution loop. But you could control the distribution loop at a lower temperature than you're controlling the boiler loop at, which basically allows you to do a reset schedule and save parasitic energy and stuff like that.
I think I talked about 10
like
minutes.
VAV coils, if you mess with them,
in the beginning,
the reheat
so
coil in the summer
probably
when it's
5
really,
minutes.
really, really only doing reheat, and you only have to deliver air that's less cold, not air that can heat the space, you can do reheat with 80 or 90 degree water. And if you start looking at, like if you use 3E plus and look at the heat loss from a pipe at 180 degrees with the right amount of insulation versus the heat loss from a pipe at 90 degrees, there's actually a significant difference, and there's a lot of feet of pipe in a building. And so it's one of those savings things that you can achieve real easily at no cost by doing the reset schedule, and the system's set up to do that. What's interesting to me about this is I'm not sure why you have the two. I don't know what value the on-off valve is. Maybe that's how they let the boiler loop warm up, but it would seem like you could do that with either valve.
Yeah.
The other thing is that when I was doing this sort of design, I would make the on-off valve the modulating valve. The boiler loop wouldn't have a three-way valve there. It would just be a loop. And then you could use the modulating valve if you set it up right. You could use the modulating valve to let flow in and out of the loop, and it would save a little bit of pressure drop on the boiler loop. It's not quite configured right to do that, but I'm thinking that might be what that two-way valve was there for. So anyway, I'll stop now because I don't want to choke. I do have a couple other things I observed at some point, but I can put them in notes too if you want me to.
Okay. If there's any that have bearing on kind of next steps, that
Yeah.
maybe they all do, and then we'll have to capture those after the fact. But I guess just since we got a couple minutes left and then we got to move on, Patrick and Mark, anything you want to ask David or the group to help you for capturing the findings list items on this system or the chill water?
Yeah, that was one of my questions is what are those two valves doing? And I think David answered some of that. The next step, I guess, is to dig a little deeper into the logic in the controls and see what's going on there.
Okay. I had a question that I think might be interesting to hear your response, David, for the group. Is the way they have it here is they've got the triple duty valve at the inlet to the centrifugal pump, which I've never seen, and I would think you wouldn't want to do. Do you have any thoughts on that, about what the implications could be?
Yeah, that actually is one of the things on my list. And also there's, a balance valve on the suction of the other pump that's throttled 80%. And the reason that's a bad idea, especially on a hot water pump, is you're taking a pressure drop ahead of the pump, and then there's a pressure drop as the water goes into the eye of the impeller. And if you look at, you could basically cavitate the pump because you set up the system to go into, develop pressure that's below the net positive suction head requirement. So it's really unusual to see a check valve and a triple duty valve ahead of a pump. And the truth be told, a lot of times when I've seen this, it's because the drawing got flipped. In other words, either the pumps are actually pumping in the opposite direction, or since it was maybe people that had never looked at this close before and they didn't really understand where to look, and they flipped their notes. In other words, the triple duty isn't on the suction of the pump, it's on the discharge. So that's what I'd go verify. Is it or isn't it really on the suction or suction? And if it is on the suction, then I would start paying attention to that, because if it's throttled, or even if it isn't, a wide open triple duty valve has a pressure drop. That could be, something that's undesirable. So I'll stop.
Okay. Well, yeah, great start, guys. We look forward to seeing what you come up with next month, and if anything comes up in the meantime that we can help with forward to the group or David or look up for you, let us know.
Sounds good. We appreciate your help.
Yeah. All right. So moving on to Presidio. So Clint, are you on the phone? Do you want to take a minute or two to kind of refresh on this PX building that you've been looking at?
Yeah, I am, Brian. Thanks. Good morning, everyone.
Morning.
So just to recap, Building 660 is the PX here on base. So kind of a smaller mall type setting, has a food court mixed in with like a barber shop and stuff like that, and a general retail area. So building was built back in 1987. So it's fairly old at this point. We have 3 single zone air handling units and then 1 multi-zone. Has a chiller with coil at each AHU, except I believe AHU 2 doesn't have cooling. That's correct. Trying to verify that. And then hydronic side, we have a condensing boiler. We have a domestic hot water heater and DDC at both the mechanical room and zone level controls. This next slide, we have, kind of brush up on our usage. We have both winter and summer electric and gas usage. You can see top left, looks like gas usage in the winter increases on the weekends, decreases during the week, and winter for electric usage decreases on the weekends. So opposite of gas, which is hopefully expected. And
The
then
orange
summer,
line is outdoor temperature?
orange line is outdoor temperature, yes.
Okay.
Yep. And then summer gas use is pretty steady on the weekends. Looks like a high, I guess base load for the winter is about 50 therms, and it's about 38 therms in the winter or in the summer. So significantly less, but I think we can do some scheduling that would help that, at least for the boiler. And then summer for electric use, pretty steady. Maybe we could recommend some schedule changes as well. It is open on the weekends, so that that's another indication of why there's gas and electric use on the weekends. Next slide, please.
Yeah. So I was going to ask the group if they could guess at the kind of configuration here, if that's okay, Clint.
Yeah, definitely.
Okay, so I guess Mark and Patrick and really anybody Team 3, since you guys didn't get to play as much last time, what would you call this airside system? And I'm being kind of vague on purpose, so you could say anything from whether it has an economizer or whether it's single or dual duct or return fan, supply fan, variable, constant.
It looks like a dual duct hot deck, cold deck.
Mm-hmm.
Multi-zone with an economizer.
Yep. And no. Yeah. So where's the terminal equipment in this? I guess.
Say again.
They're fan coil terminal boxes, right, Brian?
It doesn't look like it here, and Clint, you can correct me, but just the way it's shown, I know that Mark had said, I think that was Mark had said dual duct, and then Brett, I think you said multi-zone. So the way the dampers are oriented, the way that it's all the zone dampers appear to be in the mechanical area. I think multi-zone. So yeah, I think Brett, it is dual deck, and and dual duct if it went all the way to the zone and then there was terminal boxes mixing it. But yeah, there's a lot. I think, Clint, the color coding you did here was really great. I think, I mean, I don't know how you track down all the mess of exhaust fans that seem like they take all the air out of here and don't bring anything back to the air handler. So it's a really interesting system, and I'm wondering if somebody can guess. So given that it's a PX and a multi-zone unit, I'll ask. Let's ask Team 3 again what the difference is, or what the purpose might be for the top set of motorized dampers versus the bottom set of motorized dampers in the mechanical area. So
it looks like the top set is for mixing. Maybe temperature control. And then the bottom set, flow.
Yeah, do you see how Clint indicated the variable frequency drive on this? So with no VAV boxes and showing a single actuator motor on these dampers, then that would be I think that'd be a really good conclusion, is that those dampers are providing some flow control. I think that's not actually the case though. In this instance, Clint, do you want to explain what you think those dampers are doing? The single set of dampers on downstream of the mixing dampers?
Yeah, I mean, I think the upstream is temperature control. One's a heating air stream and one's cooling air stream, and then the ones below it, I believe, are I would imagine airflow to the different zones. But correct me if I'm wrong there.
So
Brian's got some real insight into this into this project. Just
Appreciate the help, by the way.
no, he's got some history on this system here.
well, and rather than there was some controls retrofit stuff we did, but let me ask this, and this might get to it, is why would there not be one of those motorized flow control dampers on zone 3? And this might be kind of hard to guess unless you kind of know how a troop store operates schedule wise.
Brian, this is Leavenworth. Because you're cooking usually in the food court, so you're exhausting. So you're providing constant volume air, right?
Yeah. So I think that's part of it. I think there's your that would probably drive, you would imagine, a lot of your load management and how much airflow you got to give. I think there's also so I know the intent here. Or sorry, go ahead.
Is there cooking hoods there? For like above grills and stuff like that?
Yeah, that's a very good question, and is there maybe a different way to represent that, the flow hoods versus a?
Because you can't send that back to an ERV. You have to exhaust that because it's like steam and whatever coming off your grills. There's a
Usually the food courts are...
Grease.
So here might be, Clint, one thing to add to this that might help clarify kind of the purpose of those dampers is whether there's a binary signal controlling them or an analog signal. And you could probably tell that looking in I know you found the control cabinet in that mezzanine. So I think in this case, if I'm remembering what was done, is all of these zones have vastly different schedules. I mean, some are, some run, not even every weekday. Some run till late at night. Some run only in the morning. So I think those are isolation dampers that have a binary signal and drive the fan down when you only need to serve certain zones. So they're kind of there just for sub-scheduling or zone scheduling. And I think the food court one was left off because that drives the schedule. There's no time when that unit needs to be running that the food court doesn't need to have flow for ventilation and load management.
Yeah, that's a great point. I'll verify that in the field this week. There's also a few things that I haven't verified yet. I did notice that inside AHU1, there are two different temp sensors for cooling and heating coils. So our suspicion that they are separate airstreams is getting a little bit stronger, and I want to verify that either there is, if those dampers are inside the AHU or if they're external. I'm not sure if you know if those upstream dampers are inside or external to the air handling unit.
Yeah, I could try to help you with that when you go back to the field. I'd also check to see if those temperature sensors are really upstream of the coil versus downstream.
Okay.
Is that? Would you guess?
Yeah.
Does anybody have a guess as to how you would want to do it, or how you'd expect a multi-zone unit would be controlling the coil flow? So, do you guys at Leavenworth have any multi-zone units?
The DB. We have one. We have some at the DB.
And AFI conference.
Okay.
In building 80.
Would you think you'd want the temperature sensors downstream of the coils?
Yeah.
Yeah. So that could be how it is, but if you're going back, Clint, to open the unit up and try to map those dampers and validate some of the stuff, that'd be something to check as well.
Okay. Yeah, and I also need to verify if there are dampers or not for external or these exhaust fans. I haven't been able to poke my head in the overhead yet, so that'll be my next step as well.
Hey, Brian, we had a quick question. What's the difference between the RV designation and the exhaust fans?
Clint, do you want to jump in?
Yeah, one is a relief ventilator.
Okay.
Which I'm a little unsure of what that exactly is. I don't know if anyone can chime in on that one.
So, Brian, you want me to, or?
Yeah, please, David.
But usually that's how the air from you got to think about the building uses outdoor air for two reasons. One is for ventilation, which is basically to control contamination, and that air usually is what's taken out by the exhaust systems.
It looks like it's two long runs.
So the minimum outdoor air should be, mathematically equal to the total of the exhaust flows plus anything you added for pressurization. But if you go on an economizer cycle, you start bringing in air above and beyond what you need for ventilation, so you have to have a way to get rid of that. And so you use a release system of some sort. And one approach to that is just to put holes in the release. If you have a return plenum, you put a hole in the return plenum with a release damper, and as the pressure builds up, the damper opens and lets the air go out. And so, one of my notes was, are those gravity relief dampers, or are they motorized relief dampers being worked off a building pressure signal?
Yeah, he doesn't have any.
Help clarify what that might be.
Yeah, it does, David. Thank you.
So for this one, Clint, I know there's other airside units at 660 that you pointed out. That this, I think it's safe to say, is the most complex. I would imagine is when you're filling out your findings list. Did you have anything that jumped out that you think would go on that findings list that you want to, or anything based on how that you saw in the utility data, or anything else that you think might be a priority?
I know, not necessarily to this specific to this AHU, but I know that the back warehouse area is pretty overventilated, so that would be something that we could look into. Maybe, I don't know, reducing CFM or increasing hot water flow rate through that coil. But I'm not too. I haven't really dug into the HU on the on sides of fixes in the field. I'm kind of open to suggestions at this point.
Okay, I got a question, and let's say Team 3. So Zach, Lubica, Joshua, Mark, Patrick, anybody else on the call that hasn't chimed in yet? I think I think you said, Clint, that the you got higher gas, you got kind of some gas spikes in the summer. So looking at just this system, what would be something to kind of check for down the road that might be linked to that higher gas usage in the summer?
I'd say you got a damper open, hot deck damper open.
Yeah. Can you you want to elaborate on just what a multi-zone system could do in the summer, and why that might explain higher gas usage?
You might be trying to reheat or add heat to the space that when you don't need it.
Yeah. Can this system do reheat, do you think? Chris is over here shaking his head vigorously. Do you want to
It's kind of
explain
weird.
that?
It's kind of weird, but I think it could, just based on you could remove a lot of your humidity with the cooling coil in the summer, and then you could reuse that heating coil to reheat that air after using those upper dampers. Would be my thought.
Yeah. And what do you think the reheat? Would you expect much of a necessary reheat load based on the climate and how the system's configured? So knowing that it's Presidio,
No.
and you have a lot of exhaust out of these higher load spaces, yeah. So you could do reheat. I think Chris is right. You could do reheat with this system with the hot deck zone dampers, but you wouldn't expect that you'd need too much, at least with this system that we got a snapshot on. So simultaneous heating and cooling, are you overcooling on one deck and then the other deck has to compensate, would be one thing to check for based on what you'd said about the utility data, Clint.
Hey, Brian, I have a related comment.
Yeah.
One of the challenges with the multi-zone system is how do you control the economizer? In other words, if I run that economizer to
is this what you
favor the chilled water coils, in other words, make the mixed air as cold as I can make it,
Oh, no, now it says not being
then I'm putting load on the hot deck. If I run the economizer to make, favor the hot deck, in other words, make the air as warm as I can make it, then I put load on the cold deck. So one of the subtleties of an economizer control sequence is a multi-zone unit control sequence with an economizer is to figure that balance out. The other thing that then comes out of that, if you go back to my comment earlier about being able to do reheat in the summer with all you're trying to do in the summer with reheat is make air less cold. In other words, you cool the air to dehumidify it, or because one of the zones needs that cold but the other zones don't. And you get to the minimum flow rate for the zone, or on this case there isn't, maybe, whatever flow the zone's getting, you're supplying air that's colder than the zone needs, and so now you have to make the air a little less cold. Well, that means a lot of times with a multi-zone system, you could just use return air as the reheat source. And so it wouldn't surprise me, it would take some controlled stuff, it wouldn't surprise me if you could really kick that gas consumption down in the summer by looking at that, like figuring out what the best way to operate the economizer is in conjunction with the hot deck. So I guess that's my point. It's not a simple problem, though. It's a complex question.
Okay, and then also I think it's on our do-out list to Clint to send you a multi-zone controls write-up that we did at Searle about converting multi-zone units to variable flow. And if we're right about how those dampers are only being used for scheduling right now, it might be worth looking at, just as a last thought, actually running the zone flow as variable volume, which it's not doing right now, it in the way that we're talking about it. So that might help some of the reheat stuff, I think, that we've been talking about, but also since your electricity is so high, you might get more turn down on your fan to actually run it as a true variable system. Since you've got those dampers there, it just might take some control work if they are binary there might be some different controls infrastructure you might have to run to get there, but it's all maybe right in the mezzanine. Okay, any last, I want to show your other system, Clint. Any last thoughts on or questions on this one?
Hey Brian, Robbie had one question on the mixing dampers. Are those interlocked? Or are they separately controlled?
Yeah, that's a fantastic question. So Clint, I would absolutely recommend, since you're going back to look at the zone dampers, unless you think you know that answer, to check that out. The way
we would suspect that they're interlocked, but I'm gonna have to verify that.
I can definitely say. Well, so Brett, what was your guys' thought on if they were or weren't interlocked? How that would help?
Based on the diagram, it looks like they're interlocked.
Yeah.
I guess one more related comment. A real prime target on multi-zone systems is that damper linkage, because it can get really complex. Ryan in his building has a 3-deck multi-zone with one actuator and a whole bunch of crank arms and springs that are supposed to make it all work. And when you look at that and think about mechanical stuff, the chances of that really working well are not good, which means you're using hot deck when you don't need to and stuff like that. So a real prime target on this unit is those dampers. So that's a really good observation.
Yeah. Okay. Do you want to? Let's look at Clint's hot water system in here. So we already established that there's no, at least on that system, there's no reheat. And looking at the system diagram, it looks like he's got these 4 loads. So I'm going to ask a question. I guess back to you guys at Leavenworth. What do you notice is interesting about how this system appears to be balanced?
Robbie said all the bypasses are closed.
Yep, except for
a little bit on AHU1.
Yeah. So is this a constant volume system?
Pretty much, yeah.
Well, it looks like it might have been designed as a constant volume system, but if you look at what Clint's showing about the pump information, it looks like somebody added a VFD on this primarily constant volume hot water pump, and then I think the diagram would lead you to assume then that the balance valves were closed in order to kind of make it a variable volume system. David, I know I've heard you talk about that. Do you want to? I think this would be great if you wanted to take a minute or two and talk to this strategy for converting a system over and running what was designed as a constant volume with these 3-way valves into a variable volume.
Sure. Yeah, I've seen this done frequently, and then I've actually done it myself. And the real trick is to make sure you keep enough flow up. There's 2 things you have to worry about. One is if you deadhead a pump, totally deadhead it, like no flow, the pump's still doing work on the water, and you'll actually boil the water in the pump and cavitate it and screw the impeller up and ruin the seals if it sits there long enough. You can close off flow to a centrifugal pump for a couple minutes to deadhead it and verify an impeller size without, worry about damaging the pump. But to run that way a lot, you can ruin it. So the first thing is that balance valve out there at AHU1 needs to be open enough to keep the pump from, being totally deadheaded. And my guess it is. It doesn't take much flow to do that, like literally a couple gallons per minute. The other thing you have to worry about is what's the minimum flow requirement for the boiler. You would hope the boiler could tolerate flow variation if they did this. But I think it was at the Presidio last 2 years ago where we saw a boiler that was operating on a variable flow system, but it actually was supposed to have a constant flow. It could have been someplace else. So I would definitely check, the minimum flow limit on the boiler to make sure you had it with that valve 90% closed. But it is a viable approach. If you can vary the flow on the boiler and keep the pump from deadheading, you stand to save pump energy by doing what has been done here. The one thing you have to watch on some three-way valves, one of the guys I worked at with McClure discovered this. Because of the way the valve plug's designed, you can basically hydraulically lock the valve when it tries to close against a fully closed bypass. So what we would tend to do would be close the bypass off and then just crack it open, which gave us a little bit of minimum flow at each load, which helped keep the water quality up and basically made the load response to a load change more predictable. But it also solved the hydraulic lock problem that Bob had identified when he was working on a system one of the first times we did it. So, because I'll stop there.
Okay, and just to put an exclamation point on it for Clint and Jay, there is that it sounds like from what we were hearing about this retrofit from a year or two ago, is that they didn't have a tab person come in and help establish that DP set point. It was kind of trial and error on the controls technician. You guys can correct me if I'm wrong, but to me that sounds like a really good opportunity to go in there as part of this effort and validate what that DP should be, and then maybe even look at resetting the DP, since you don't have a lot of valves to report back and give you that information.
Yeah, could be. Yeah, say that again, Dave.
I was going to say, it could be the DP sensors are far enough out in the system that if you just controlled for that DP, it'll automatically, because of the 2/3 rule thing, make what you need at the pump to accommodate the other valves. So you may not need to reset it if you fine-tune it. And this is a fairly small system. And I may be getting too far in the weeds, but sometimes you need differential pressure at the headers that you then reset based on a remote signal to get rid of the lags associated with the transportation delays. That's a bigger deal on VAV systems than it is on pumping systems, though. So I'll stop at that unless Brian wants me to go into it some more, or I can go into it a different way, in a email or something.
Yeah, we'll make a note about that, and if this turns out to be one of their focuses that they put on their findings list and delve more into, then we could try to get them those resources.
Thanks, Brian and David. I think I'd love to pick your guys' brain on the side, maybe on a separate call with Jay, on thoughts on rebalancing the system and just low-cost, no-cost measures, because this new hot water pump retrofit is kind of a hot ticket item because it's already been installed. We really just want to tweak it into place. And using Grant, our controls guy, and some of the boiler techs here, I think we can easily do that with your guys' help. It'd be awesome.
Yeah, I think you got a great project, so we'll do what we can to help, and we'll get you that, our take at least on, what some of those priorities might be to look for this month. And yeah, great job. Look forward to seeing what you come up with. So,
Hey Brian, can we ask a quick question real quick? David, can you give us a 30-second explanation of the 2/3 rule?
Yeah, it's a rule about putting the sensor 2/3 of the way down the pipe. So that's the short explanation. Basically, the idea is the further away from the pump you go, or the fan, the pressure sensor basically sees the pressure drop in the distribution system.
You can completely blow past this stuff if you want.
On the system diagram we were looking at,
valuable if you want me to just go past it.
If the pressure drop from the discharge of the pump out to AHU1,
do you want to keep going with the questions?
Let's hear it. How can I say this best? Say AHU1 represented 50% of the load, and AHU2, 3, 4 represented the other 50%. Hey, Brian, can you flip back to that? There you go.
Oh,
Just put that up for a second.
this one, David?
Yeah. So pretend AHU 2, 3, and 4 are all connected to a T that's, the piping from that T to the units is identical, and the bulk of the piping in the distribution system is from the discharge of the pump to that first T. In other words, all the air handlers are in the mechanical room at the far end of the building. And so you have a long run of pipe to the air handlers and then short runs from a bunch of T's to each of the coils. Does that part make sense to everybody, just as a visual in your head?
Yeah.
Yeah.
Okay. So then pretend AHU1 represents 50% of the load and the other 3 units represent the other 50%. So on the design day, say you needed 10 feet ahead to get the water to go from the pump to the mechanical room. And then if you held 10 feet at that T in the mechanical room, you could get design flow through all the coils. So that would mean if you were controlling for the pressure in the supply line, you would need to control for 20 feet on the design day to get 10 feet at the mechanical room, which satisfies the coils. Does that make sense? Anybody, or does that not make sense to anybody? All right. Now, if we shut down AHU 2, 3, and 4, we've cut the flow rate in half, but we still need the 10 feet because AHU 1 is still at full flow. So we need 10 feet at that T, but the square law says instead of 10 feet to get the water from the pump to the mechanical room, we now only need what? In other words, that 10 feet of pressure drop from the pump to the mechanical room at design flow, if we cut the flow in half, how much pressure do we now need? A quarter of it. Like the square law says, P new equals P old over flow new over flow old. The flow ratio went to 1/2. Flow new over flow over squared. The flow ratio went to 1/2. 1/2 squared is 1/4. So now we only need 12.5 feet at the pump to give us 10 feet at the mechanical room. If I'm controlling for discharge pressure at the pump, I always have to control for 20 feet. If I control for discharge pressure at the mechanical room, to get my 10 feet, I'll force the pump to 12.5 feet automatically. So the further out the system you go, the more you've optimized the control of the pump. But it introduces a lag into the control process. And so I'm taking too much time, so I'm going to stop for now. But I can go into that more later somehow.
Well, I think if there's a kind of technical paper or a really good Asher article that kind of visually, I know I had one at some point, David, but
yeah, there's a blog post. I did a string of blog posts about this. So, yeah.
We'll find.
I should have just said that.
No,
I'll send you the link.
That's that's really helpful, and we'll get that out to everybody. Okay.
Hey, Brian, I got a quick question before you leave that slide.
Yeah, sure. Real quick, and then we got to move on to Chris.
What's going on with AHU3? It looks like it's different configuration there than the rest of the air handling units.
In which way?
Two inputs.
Oh, the dual inputs on the coil?
Yeah, it looks like a double pass.
Yeah.
Probably
Could be two coils stacked up. A lot of times you make a big coil by putting two smaller coils together on top of each other or beside each other. I can send you some pictures of that.
Okay, thanks.
Okay, I'm going to pull up Chris Battisti's building here at 699 and let him give a quick overview, and then we're going to show you his very exciting airside diagram and see if you can pick apart some of its quirks.
The many iterations.
Yeah.
So we're doing, me and my team at Leavenworth are doing building 699, which is a chapel. Here's a quick overview with a kind of a picture from the side. And we did, in the last setting, we did a full analysis on the meter data, pretty low base load, and it seemed, this is just 1 week example, but it's a pretty consistent from day to day in terms of peak loads. And looking at the scheduling, there seems to be some potential there. But going on to the system diagram, third iteration on this one. So basically splits the building in half with each air handler. So each air handler kind of feeds the main religious space in the gymnasium type area with a and then they also each feed individual like classrooms and offices, and then the returns come through the hallway. So I guess I'll ask a couple questions to start with Presidio. Looking at this, can you determine like how do we get ventilation to the space?
And I'm going to zoom in because they're like Chris said, they're kind of mirror images. So if you just look at air handler 1 on the top.
Yeah, I'm sorry, it cut out during the question part of that.
So like just in what way do we get ventilation to the spaces from outside air?
Yeah, I see above ceiling return air. You're talking about the mechanical. Yeah, you're talking about AHU1 then?
Yeah, outside air.
Okay. Yeah, it looks like it comes in through fire damper and a damper. Almost looks like some sort of economizer setup. Is it just being brought in through the roof?
It is, but like one thing I've been staring at a lot is there's actually 2 ways to get from the same outside air duct to get outside air to the air handler.
Through the heat wheel as well?
Yeah.
Okay.
So why is that a way to set up this system?
Maybe heat recovery through the heat wheel might reduce energy demand on I guess your heating demand.
So
that's the first thought.
So why would we need the other one then? Because we don't necessarily need to run the heat wheel to pull outside air.
What about humidity?
Yeah, that's a good point. So I guess the question I'm looking at when I looked at this is if the humidity is a great point, which is another reason for the heat wheel, but then why would I want to pull pure outside air without going through that heat wheel?
Well, if you don't need to heat and you need to cool, wouldn't you just need outside air?
Right.
Okay. Is that for your minimum intake?
Yes. It's an interesting setup to me.
Yeah, it is.
Because like usually I've seen there's like either it just goes through the heat wheel, and especially with our climate, we just don't. It's either really hot, high humidity, or really cold. A lot of the time, there's a little bit of a shoulder season, but it's just kind of interesting how they set that up.
You want an opinion?
Definitely.
Okay. I'm pretty sure the heat wheel is your minimum outdoor air stream, and that other duct is for if you wanted to use the economizer.
So that's kind of.
In other words.
Go ahead. Sorry.
Yeah, go ahead. I think you got it. Yeah.
Yeah, that's what I was kind of thinking too, and I've been staring at it recently. I'm not there anymore, unfortunately, so I can't stare at it in real time. But like lately, it's been using that straight from the outside air a lot. And actually, we had some issues with pulling enough CFM to satisfy the zones because it was doing 100% outside air.
David, would duct sizing be one clue in the field? The relative difference between the outside air that bypasses the heat wheel versus the duct size discharging from the heat wheel? Would that help give a clue on if that is the design intent, that you're pulling a lot more air, if that is an economizer air path?
Yeah, or it would be a clue about whether they thought about it right. In other words, if they really wanted a couple things. Like once the economizer process starts, is there any reason for a minimum outside air, or basically the significance of minimum outdoor air goes away because now you're using more than the amount of outside air that you needed. So if I was going to, just thinking about it out loud, if I was going to do this way, what that kind of means is once the economizer process starts, I would just quit using the heat wheel and just use outside air. Well, that means you'd size that duct that goes around the heat wheel for the total system flow rate. So that you could basically shut down the heat wheel, take all those pressure drops out of it, shut down the supply fan, and just use outdoor air for an economizer process. If they only size that duct for the difference between the minimum outdoor air, like 8,200 CFM and 19,000, then that could be a problem if they actually shut down the heat wheel and try to pull the outdoor air that way. So I think you're right, Brian. That duct size is going to tell us something. I think you can make a legitimate argument for, okay, they got a duct. When you're on economizer, don't just shut down the heat wheel and save all that energy, the cost of running it and the pressure drops. But for that to work, the outside air duct has to be big enough to support the economizer.
Can we ask the team, because I think there's a really kind of key thing that Chris saw when he was out there that may touch on this. Let's say so team 3, what David's saying is if that economizer ductwork wasn't sized for the total airflow through the air handling unit, what would be an indication of that when he's out there in the next couple weeks? What part of this, where would you look in the system as an indication that's a problem, that they may not have sized that duct right? I'm trying to get at your pressure, like that you saw that the.
Yeah, I think I was just gonna say it because it.
What?
Yeah.
I've got a comment here from Presidio.
Yeah, go ahead.
I was thinking just off the top of my head, maybe you could turn off the heat wheel, bring in outside air, I guess, and try and get full flow through that duct, and then check the DP on the discharge side of the fan.
Yeah, so Clint, I think you hit it, or go ahead, Chris.
Yeah, so what's great is that actually happened on its own.
Oh, nice.
So yeah, it was Kevin Heim, who's the HVAC lead on my team, and I stared at it for a bit, and I was looking at the controls. So I forgot what that DP was set at. I think 1.5 inches, but the supply fan. So there was no return air coming from the mechanical room. It was 100% outside air bypassing the heat wheel, and it could not satisfy the CFM requirements. We were hitting about 0.3 inches instead of the 1.5 inches that we needed. So a lot of dampers were going 100% open, especially the ones in the religious space / gym areas that need like 2,000 CFM. So it was providing the right temperature pretty well, but it just could not meet the CFM requirements.
Is there question here? Is there any way to, I guess, how do I put this? Increase the heat in the heating coil, I guess, temperature of the water, and then decrease CFM to maintain space temperature without, overloading that duct?
I'd be more worried about, I guess, making sure I hit my minimum ventilation, which I think off the top of my head, I don't think it was hitting that 8,200 CFM.
Gotcha.
Because it was hitting the temperature needed, but the spaces still needed cooling or heating, and it just wasn't getting enough air in there to do that. And we were at a point where I think it was asking for 55-degree air, and it was pretty satisfied in terms of temperature, but barely below. So I think that'd be kind of tricky. But yeah, my primary concern was on the ventilation side.
I'm just thinking about this out loud, Chris. Let me reiterate what I think you said, because I was thinking about something and I might have missed it. But you said you've actually seen it try to use the outside air that bypasses the heat wheel, and they shut down the heat wheel and close that. It looks like a damper on the discharge. Is that what you said?
It closed the damper on the... Yeah, closed the damper on the discharge of the heat wheel, and then also the damper was closed for the return at the economizer for the return. So it was 100% outside air.
So we can actually use damper.
trying to go 100% outdoor. Wonder what would happen if you overrode the damper on the heat wheel open and just let the system use the heat wheel as another airflow path.
So David, can you say that again using we were going to ask folks to count how many dampers were in the system that could be modulated as part of control? No, I mean, I think with the time we got, I think you're onto something. So can you rephrase that using these damper designations that we just made up so that we could all kind of track what you're asking?
You mean ask it as a question or just say it?
No, yeah, you can keep going how you were, but just are you talking about damper like on the screen, damper?
Yeah.
3A,
Oh, okay, I'm looking
up
at my screen. I forgot to look at yours. Okay. Yeah. So I guess what I'm saying is open up when it's in that mode where damper 4A is the only damper open and damper 6A is closed because the economizer is saying, hey, I want all the out there air I can get. Just override damper 2A and 3A open, and now you basically put a duct in parallel with that other branch, and you may be able to pull enough air through that heat wheel without running the supply fan to make the system work in that mode. The thing you'd have to watch then is the supply fan will probably be spinning, and if it's not spinning in the right direction, or even if it is, if you tried to start it and didn't have the VFD set up right, you could blow up the VFD because of a bunch of things that can happen that I won't talk about now, unless somebody tells me to.
No, let's talk about that at a time because that's an interesting thought, and that's one of the things I want to talk about is how could I get this figured out, but. I had one more question for the group, and so one other thing that kind of was stuck with me and the team was, could someone kind of go through the system kind of from outside air through one VAV in the zone, how many heat exchanges can happen in this system?
This many? I don't understand.
Okay, so this is Zach. So it looks like you could, at a maximum, go through 3. 1 at the heat wheel, 1 at the, I'm just going to pick the religious space, 1 at air handling unit 1, and then final coil at the VAV box in space.
So that's true. So, but one thing is, coils aren't the only way we're going to heat transfer, right? So is there any other way to get heat transfer into this system?
Your above ceiling return.
I think he's getting it like direct mixing rather than through a heat exchanger. Kind of adds some additional quirks to the system. So we did this yesterday. Is it okay to?
Yeah, go for it.
So we did it yesterday, and we found 7 places, that an air molecule going through the system from outside air to the zone. Ideally, you're operating the dampers and the valves on the loads and the heat wheel in a way that you're not doing 7, a sequence of 7 different heat exchange operations. But it speaks to the delicate complexity and kind of dynamic nature, I think, of this system, that there are 7 places that you could have heat exchange. All the places that Zach said, and then the places that Chris had mentioned where you have the potential for direct mixing with that economizer, bypass coming at the discharge of the heat wheel, the 2A here, with the kind of, I guess, classical economizer mixing plenum that looks like 3A. So there's a lot going on here, and I know we don't have a lot of time, but, and so Chris, any questions you want to ask, but I would think a question to ask David is, in addition to just reacting to this system, which for a number of reasons is now my, I think, favorite airside system diagram of all time, but how do you approach going to the field and even kind of generating a findings list? Because it just seems like you could get lost in so many places. So
yes.
David, do you have a reaction to that, or any words of wisdom for Chris and Kevin and the team?
Yeah, I'll react to that, but I also have one thing I want to point out that could be important too, so I don't want to forget to do that. When I start to feel overwhelmed, which happens a lot, I start trying to like focus in. And so, if for instance, like, you know, you have a central air handling system serving multiple zones. And so, like, actually, this might be a good way to illustrate. I was just having a discussion with another student from the Energy Center who's looking at a big system with multiple zones. And Ryan had sat down with him and run the zone diagnostic in the UT, and it said all the zones were messed up, basically. And so Isaac was like, well, how do I start? You know, there's all these zones. And so I said, well, the first question is, are the zones really messed up? Because, you know, the UT is only looking at data, and is the data right or not? So I said, why don't you go out, take an infrared gun, and just sort of shoot the diffusers on the zones and see what that says about aren't you reheating, what's going on there. And you could, by doing some broad, and don't hit every zone, just say I'm going to sample, there's 25 zones, I'm going to sample 10%. So I'm going to, there's 50 zones, I'm going to sample 10%, so I'm going to have 5 zones. And if you hit 5 zones and they're all reheating when they shouldn't be, then you sample another 10%. And if you discover all these zones are reheating, then the question is, well, is that because, or not reheating, there's warm air coming out. You don't really know it's reheating. Is that because the supply fan is not delivering cool air, or is that because the zones are reheating? And if it turns out that it's because the supply fan's not delivering cool air, there could be stuff wrong with the zones, but the first thing to do is figure out what's wrong with the supply fan. Because if the supply fan's not delivering what the zones need, the zones can't work anyway. So if you take that example and like pull out like the bullet points, I think what I'm really saying is, you're starting to look, field verify the system diagram if you haven't. If this isn't field verified, field verify it, because that's going to tell you, is my data right or not? If you're looking at data from the EMS in the context of the system diagram, is the data believable or not? So do some sampling, see if you really think what you're seeing is right. And then once you start looking at that data, let that focus you initially on where you want to head. For instance, if all the zones are messed up and it's because the air handler isn't giving them what they need to look at, go back and look at the air handling unit. And in this case, you look at the air handling unit and say, well, it can't get what it needs on 100% outdoor air on the economizer cycle. Well, before I can ever fix anything else, maybe I need to address that somehow. So is that helpful? I hope. Maybe. Is that what you're thinking of, Brian, when you asked me that?
I think, so what I got from that is, I think, David, is I kind of, because I look at this and I'm like, where do I even start? But I think it's a good point I kind of want to start looking at the zones more and maybe work backwards, because my inclination typically is to look from left to right. Does that kind of make sense?
Yeah. And it doesn't mean you shouldn't look from left to right, because we already know you want to look from left to right, right, because of the outside air thing. But we know we have a problem with the air handling unit. If you look at the zones and the zones aren't working because they can't get enough cool air, then maybe that makes solving that air handling unit more important as a first step than if they are getting cool air and they still aren't working, right?
Right.
And if it's 2 or 3 zones that aren't working out of 20, that's different than 18 zones that aren't working out of 20.
Okay.
And so if you can do some simple sampling and sort of quantify things, for me that seems to always help. Is the data valid? Is the picture valid? Is it a big problem, universal, or is it a problem that's focused in certain areas?
Okay.
This is kind of important, just real quick. If you can go back to that system diagram. Basically, the coil and the air handling unit's in the reheat position. You already have reheat coils at the zones, so I think that was probably a mistake. So you want to make sure it's really there. Basically, if you do, I just did a quick conservation mass calculation. You could get freezing, if this heat wheel failed, you could really, on an extreme day that's conceivable in Fort Leavenworth, you could have a freezing mixed air plenum. And so having that heating coil after the cooling coil does you no good in terms of protecting the system. So I'd look at that close. Is it really after the chilled water coil or not? And if it is after the chilled water coil, what are you going to do to keep the system from tripping the freeze stat or freezing a coil in extreme weather in Fort Leavenworth? Because if you look at the flow rates, it could do that, especially if you're maintaining that minimum flow while the system flow is varying.
Yeah, I think, and just real quick, so me and Kevin did this entire system without looking at it. We did it field verification fully. But that's a couple of good things to double check because, yeah, me and him stared at this for a while, especially with the freeze stat in the middle, because that's there, we verified it. So yeah, we need to dive into it maybe again.
But David, it's worth noting, you guys also said too on the team call that this was in the as-built, or maybe it was the design submittals that you had.
Yep.
This seems to be the design intent, David, that they put the heating coil, that they put it in a reheat position, even though they have fan-powered reheat boxes, so it wasn't.
Yeah, so it's so they probably built it the way they wanted to, and I'm saying they may wish they hadn't. Like, if you think about that, the freeze stat after the chilled water coil is a bad plan right there. You're protecting the wrong thing. But they may have put it there because it kept tripping on them.
So does that mean that that a possible measure to investigate is potentially valving off this heating coil if you recognize that it doesn't have that freeze protection function, and if you show that the reheat coils have enough capacity to pick up the design load coming from the mechanical room through this all these airside places?
Well, yeah, except they probably don't, because like my quick math said on like a 10 or 15 degree day, if the air handling unit was at 19,000 CFM and you still were bringing in 8,200 CFM minimum outdoor air, you'd freeze the coil. And since the VAV system on that day, this air handling unit probably isn't doing 19,000, and the heat wheel probably is, so the minimum outdoor air percentage is approaching 100% outdoor air. So way above that extreme condition, you're going to generate a potentially freezing mixed air plenum. And so, after you froze the coil, you wouldn't be able to heat the building because the reheat coils probably aren't set up to deal with 30 or 40 degree entering air. So it's an operational issue, not an energy issue, but I'd be really concerned about that in that environment.
Hey, Brian, Robbie pointed out that the cooling coil is a glycol system.
Right.
Oh, okay, well that helps.
Okay.
25%, yeah.
He also said that the ERV has a lockout low limit.
Yeah, you're counting on that working to give you the preheat. Right. But if the ERV shut down, now you got that other outside air. I just would be worried about it, I guess. That's all. My frozen coil alarm went off.
You still also have that return air duct.
Yeah.
I think it goes to Brian's comment about how complex this system is. There's a lot of things that could go wrong on you.
There's a lot of dampers in there.
Yeah, and maybe the point, I mean, because that's my knee jerk is to kind of brainstorm the solution for it, and maybe the biggest thing is just to note that as something to delve more into at this point, to say you might need a better freeze protection strategy. So maybe you do something like when you lock out the ERV or your mixed air temp sensor says you're approaching that, anywhere near that freezing condition, accounting for the glycol, maybe you interlock that where you just lock out outside air and bring in your return air, just so maybe there's some fail safe, not for energy but just for operations that comes out of this that you just flag for now as something to take the rest of the time to, so the plan is like make a list of the stuff to look at. The next month is kind of prioritize that list and make a monitoring plan for what data you'd have to gather with your ALC system or with portable data loggers. Then you go get that data and find ways to process it and present it. Then we do the calcs or the implementation stuff. So we got time to hopefully think through those things, but I gather there's going to be a lot of those with this system. So freeze protection strategies, maybe one of them. I know we're a few minutes over. I know Chris wanted to show the chill water. I'll leave it to you if you want to take a few minutes to do that, or if you want to do kind of end on this point.
Let's just end on this point. The chill water is not nearly as interesting.
Okay. It's the mother of all airside system diagrams. So, yeah, lot to follow up on this. So we'll try to help you, and we can maybe help support a site visit, or if you need more data loggers for this, or relaying kind of some more things that you're finding with David, or supporting some of the functional tests for where you get the air and how that changed your pressure readings. Yeah, this is a great one. So.
Yeah, it's really well done. I mean, the fact that we can come up with all these questions so clear, it's very cool.
Yeah.
So.
Okay.
And I just want to point out that we at Fort Leavenworth have now contributed 2 very complex airside systems in 2 years. So we're trying to raise the bar on complicated mechanical systems.
Center of HVAC Academic Excellence. I think that's the title to shoot for. Yeah, no, but in all seriousness, I mean, not to keep harping on it, but I think a major output of this is to really, not that the core is going to be easy to make a momentum shift on their design practices, but I think you're gathering enough really clear bad design strategies implemented at Leavenworth that you can really throw this in their face and say that we need to make sure this isn't happening on our newer buildings and our retrofits. We need to not have such conflicting design strategies for what we do with outside air and exhaust air, and pick one and really make that a flag in the design review processes to try to catch this stuff before it happens again.
Well, and I think on a side note, that one of the problems that we have is that reviewing these designs without system diagrams that break down system flows like this does is exceedingly difficult. Once you put everything in a diagram like this, it's a whole lot easier to see how complicated the system is.
Yeah, absolutely. Okay. Any closing thoughts from anybody on the call we haven't heard from, or anybody listening in? I want to make sure we get to hear from everybody. And I know there's still some people that are playing catch up, and some people that we have to get feedback to. So we haven't forgotten about you, and we'll be following up in the next week or two with some of those comments and next steps. But I think this is a great call, and hopefully it's time well spent on your side, and we can continue supporting and making progress on the projects. So yeah, if there's nothing else, feel free to keep shooting us emails with stuff that comes up and submitting on MillSuite. But yeah, great call. Keep up the great work.
Thanks, everyone.
Oh, I will point out that just before everybody leaves, we are going to have a bonus system diagram from a deep energy retrofit project that Jay has. That there's some, and the people are leaving, and there's some system configuration changes that they're proposing that we're going to look at real quick. So we're going to stay on the phone if anybody's interested in more system diagrams. We're going to look at that for 20 minutes. So you're welcome to stay. If not, we'll be setting up the team calls for at the end of this month. So thank you, and yep, thanks guys. We'll see you next time. Okay.
Who could possibly not be more interested in more system diagrams?
David, just real quick. So from my original iteration to that one, I think, so I came up here Monday and Brian consistently was like, you should add this. Irene
shares a lot of the blame, to be fair. We were kind of, the 1-2 punch. It was, well, if you're showing this, you should show this, and it sounds like you're saying the air path is really this way. So
It took a lot.
yeah, iterative. Yeah, they're iterative. But no, this is.
Well, that's how it works, man.
Yeah.
Well, it was fun, but it was pretty funny. He's like, one more thing, and I'm like, it was one more thing 3 things ago. Like, all right, like.
It's we're gonna frame this and put this on your wall at some point, Chris. So, all time well spent. Yeah, Jay, I love you gotta love the enthusiasm. I think it was the timeliness of, as I was saying, if anybody wants to stay for one more system, Dia, click, 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 click. So that speaks to the enthusiasm there. So Jay, if you want to drive, I got the PowerPoints I can build up, but I think you are in the best position, you and Gwen, to kind of talk through what you want to do to prep for your call today, and we'll try to be on there too to help you out. I sent some additional system diagram write-ups like we had talked about to kind of show those 2 scenarios. But why don't you give a little overview here for anybody on the call and for David?
Hey, Brian, actually, I think Jay had to step away.
Jay was one of the guys that clicked off on his own call. Wow, that hurts.
Yeah, and I don't know if Gwen is on the call today.
Okay.
It looks like it's just me.
Okay.
What do you think, Clint?
Yeah.
So look at
yeah,
this
what
and
the
tell
heck?
us what the answer is, Clint.
This is a very, very intricate system. And, you know, Jay showed me it my first week here, and I was kind of blown away.
I've been looking at this for 3 years, and I'm still blown away.
Yeah, I'd love to know the fix on this one, to be honest.
Well,
so Brian, you might have the most information out of all of us.
okay. Yeah. So, well, what I can do, David, because I don't want to, I don't think we have to wait, and we could probably capture your immediate reactions. Might be helpful to relay to Jay and Gwen. So this was a what was termed a deep energy retrofit. And I think Jay and Kapil have presented on this at the quarterly EBCX calls at Pacific Energy Center.
Yeah, I was thinking this might be that system.
And I know Kapil had his own system diagrams. I think they've gotten a little more detailed, and the big change is that the project technically finished about 2 years ago. It's been occupied for 2 years, but Jay has been fighting for 2 years to say that all the data from the JCI control system they put in there is telling him that they are not meeting the RFP required 70% of the domestic hot water load, the design domestic hot water load being provided by the solar hot water collectors on the roof. So it's a kudos to his, how resilient he is, the government bureaucracy, and having to make this fight for so long. What we've tried to do to help him with that, and Gwen has been stepping up and helping on the core side at the project office, is to say that this sheet, this controls schematic that the designer AECOM has been using to try to communicate what control strategies and what problems do or couldn't exist. We've been trying to communicate that this isn't really the right document or diagram to do that. It is a simplified schematic relative to their actual piping schematics, but there's just so much here that we've tried to separate this into loops. And now that Jay has gotten AECOM, and Jay and Gwen and I think their project office there has been supporting Jay, but they've gotten to the point where AECOM has admitted that this system is by design unable to meet that 70% requirement, and they're now brainstorming on slight configuration and controls changes that could help them do that. So I could, maybe in 15-20 minutes, I don't think we're going to have like yes, this is, for how complex the system is, this is the one thing you can do, but maybe we can get your reaction to some of the changes suggested, and you might have some cautions even that I think will be valuable for Jay and the team.
Okay.
So the first thing to recognize here is just some of the major systems, and then we'll show how they break down into different loops. But if you're a slug of water that's coming in from the domestic water supply here on the left side, just to be aware of all the places it can go. is half of the building has this gray water heat recovery that there's actually a pump here that isn't shown. This isn't the fully updated diagram, but there's a pumping system and gray water heat recovery for the showers that the domestic water can go through, or it can bypass that if temperature sensors tell it that nobody's taking a shower. Then it can go and link up to past these circulation pumps that should be off when the domestic hot water is coming in, through these strat tanks. So there's a heat exchanger and a loop that the domestic hot water can come in here. Strat tanks are in parallel, goes to this 2,000 gallon holding tank. When the holding tank cools down, it can recirculate water through the strat tank. So the only heat exchange for the domestic hot water is in these stratified hot water tanks. There's a sidearm heat exchanger in both tanks, so parallel still, for the solar hot water collectors. And then there's another loop for the heating hot water, they call it, that goes to the zones to low temperature radiant panels in the ceilings. And that water is meant to be reset from 100 to 130 degrees Fahrenheit through a mixing valve here on that side of the system. And there's also booster boilers that can heat the strat tank up when there's not enough load from the solar. I think there's probably some other nuances there, like there's domestic hot water return pumps in there, and some other probably details. But the main problem is that the way the system is designed is that these strat tanks have to be kept at between 140 and 150 in order to keep the domestic hot water tanks at 150 per design. So in order to capture adequate solar hot water to meet that 70% requirement, it's very difficult for them to do that with these strat tanks being set so high. And these condensing boilers are never in condensing mode because the inlet to them from the strat tanks never gets low enough. So that's a very broad view of the problem, and I think that'll be a little bit more, a little bit clear, not completely clear, but a little bit clear in these diagrams that we kind of broke down. So this is that, we've kind of segregated by loop, which we thought was helpful for Jay. So this is the solar hot water loop. And this red valve here is kind of one of their proposed changes. So I guess before I get into the changes, I'll just show what's there right now. So this is the solar hot water loop, not very complex.
Are those boxes to the side of the stratified tanks, they actually have a heat exchanger in them?
They do, yeah. Yeah. Okay.
And so, and the circulation from the stratified tank through that heat exchanger is just by gravity?
It's part through the stratification effect and part through the force flow from the radiant panel loop.
Those three lines represent the interconnection, and the three lines are basically going to a heat exchanger inside the box by the
Correct. Yeah. So the side
tank.
Yeah, the side arm is, and I think at some point in some places we show that as like its own kind of loop. So it's kind of a shell and tube where the tube is the solar loop and the shell is water that's allowed to enter this side arm through these four lines.
So it's vertical like that, and so it has to be the density difference that makes the stratified tank water go through there.
Yeah. Yes.
Okay. I'm just making sure I understand it. That's all.
Oh yeah, and when you understand it, please let us know because we're still working on it. So
you didn't. I don't have these, right? These slides.
I'm sorry, I don't think I put them on the Google Drive, but I can if this. So this is one of the class projects. This is Gwen's project that we're helping her with. We didn't think it was ready. It's so complex. We didn't think it was ready to be shared with the class. But it did have a little bit of urgency because of this configuration change being discussed with the contractor. So we're helping on the side, and maybe next month we might continue to work on this and show it to the class. I think it's a great. It's a great one to look at. It just, I think today was fairly interactive, and we'd really have to think about how to make this interactive to get people to want to participate in the discussion on it.
Yeah.
So a separate issue for maybe next month. But this is the boiler and the radiant panel loop, and what we're trying to show is how there's the elevation changes in the ports with how water, where the inlets and the outlets are on the strat tanks matters, and we're trying to show that. And things like where the check valves are and how they have the mixing valve that's meant to control temperature to the radiant panels, how the booster boilers are going to be taking in a lot of warmer inlet water because of the overall storage of the strat tanks. One thing I don't think we show is we do have multiple temperature sensors in the strat tanks, so we do see a little bit of that where there is stratification, but it doesn't seem to be happening a lot because the boilers are working so hard to maintain that 150. So that's the...
Are the strat tank volumes large compared to the flow rates that these pumps can produce?
That is a good question. I mean, I think that they are... I think they're relative low. I mean, compared to the domestic storage, that's definitely where most of the volume is on for where the heat exchange needs to happen, but I don't know the answer offhand for volume.
Because that in and of itself could work against stratification. I mean, just to be silly about it, if the tank was 120 gallons and you have a 120 gallon per minute pump, it's not going to stratify very well, probably.
Right. So I'll try to, so we should probably get the GPM, at least the nameplate or design data on these pumps that don't have pump names, we found, and see how that compares to the Lochinvar strat tank storage numbers to at least see what we're up against. And then the real, I think most of the changes that we could show is what they're proposing on the domestic side. So what we're trying to show here is this kind of loop inside the stratified hot water tank. So it kind of looks like a typical hot water heater in the sense that it is this kind of coiled tube. It just has a lot more, I guess, density of tube bundle up at the top. I imagine because of the stratified, the kind of hot water, the intent of these devices to have hotter water at the top of the tank.
Mm-hmm.
We're almost ignoring the GFX system, the gravity fed heat exchangers that are underneath the buildings that are intended to capture some of the hot water and preheat the cold domestic water coming back in. It doesn't seem like from the initial data like they're doing much, and just for simplicity's sake, nobody's looking at that too carefully. What we are looking at is how water, this recirculation loop from the 2,000 gallon storage tank underneath the tank with these circulation pumps, and how that can feed back in there in order to, I guess, circulate just when the tank is sitting and it needs to be reheated, or when the domestic water initial run through is not enough. And then pretty typical, I think, domestic hot water recirculation pumps. So this is the domestic side. So if none of that makes you want to jump off the call, David, I can go through what the changes are, and that might, maybe some alarm bells might go off on some things for us to ask them about or check.
Sure. One random thought when you were talking about the GFX, is there any way, like when you said they're under the building, I thought, are they buried? I doubt it. But really, what that led me to, is there any way those could work against it? In other words, they could actually be taking energy out of the system inadvertently?
They could. So there's the intention is that there's a temperature sensor at the GFX that we probably need to show at this diagram, and as this gets cleaned up to kind of indicate a little bit of what we suspect with the control sequence. But I know that the intent is for that system only to run when the GFX sees that there's a certain temperature hot water being drained from the system.
Okay.
Okay, so there's a fairly simple change, I guess, that they were suggesting making on some of the loops, and then a little bit of a more extensive change on the domestic hot water side of things. But the essential solutions being discussed is to see if you could have these tanks where one is essentially a preheat tank that's kept at a lower temperature so that you could get more load out of the solar collector systems, and also pull the boiler inlet from the colder tank, the preheat tank they've been calling it, so that you can, when you do need the boilers, run in condensing mode. So a lot of the changes that they're suggesting separates those tanks in a way that you can do that. And on the solar side, all they're suggesting is this three-way valve, this diverting valve, so that they could pick which stratified tank they want to load up first. On the...
Here's a random thought reaction to that.
Sure.
Has anybody thought about putting them in series?
Yes.
Okay.
So that's one of the discussions, and that maybe it's worth jumping to that. So I'll just to convey that there is a change on the hydronic side that's maybe worth circling back to, is that this is how it's pumped right now. This is what the configuration being discussed would make it look like, where you're essentially putting the boiler in between the strat tanks on the heating hot water loop side of things. So that's another change. But they have two scenarios that they're suggesting for the domestic side that would determine if they are in series or if they're in parallel. So the feedback that we've given Jay so far is that the scenario that has them still in parallel but puts these binary discharge valves at the strat tank is less preferred. And the reason that we said that, and I gave him notes on this a couple weeks ago, so I'm a little rusty, but I think the concern that we had is that you could almost never use, if you pick one of these to be the preheat tank, that you keep it like 90 degrees, say, so you could scavenge more out of the solar hot water loop. The concern we had is that you could almost never use that strat tank, because you'd always, even if there were modulating valves, you'd always need to get defer more to the hotter tank that's kept at 150 in order to keep this at 140. So say that you had cold water coming in because they're using showers. That means that in order to replenish the tank, because this is the only heat exchange to heat water to deliver it to the storage tank, you'd have to use more from the hotter tank. And if you were recirculating from the 140 temperature tank, then you'd still have to, it seems like, use the hotter tank more, because you'd just be cooling it down by sending it through this tank. So this scenario didn't seem like a good solution to us based on that understanding. Is there any reaction to that, or is that, would you concur that that seems like that doesn't buy us a whole lot?
Yeah. My reaction is, wow, this is really complicated. I need to think about this. But what you said made sense to the extent that I've absorbed the system.
Yes.
So.
And I should say that this isn't field verified, and it leaves out a whole lot of stuff that we know that needs to be documented in here that may be important, that we're assuming for now in these initial conversations that it's better than that design M807 sheet that we first showed you, that it's better than that, but that this needs to be, we need to make this their responsibility to agree that this is a better way to look at the system, and then field verify and add and edit to the system with our help, and then make the change and do the test to verify that the change would would be beneficial, and then make the change if there is one.
Yeah,
to be made.
I absolutely agree with that. You need to get to where you know what's there and you can understand it.
Yeah. So I know Gwen's
Otherwise,
done
you're
some of
just
that.
changing an unknown.
Yeah, and I it sounds like Gwen's done some of the field verification, but a lot of it, to my knowledge, is just taking what's on M807 and reformatting it in this way that makes it a little bit more digestible. But so we need to get with her to find out what's been field verified, and at some point we'll probably go out there for a site visit and sink our teeth into it more. But the other scenario change is to have them more in series in this way. So where you have the parallel, where you have that first T, where you can go to each tank, capping that, and having the first tank. So in this scenario, it'd be tank 2 would be the preheat tank. And at first glance, this seemed to be a preferred solution because it really does allow you to use the tank as a preheat tank. And then if you've put enough solar load into this thing, and that's enough, or it's somewhat enough, then you can send most of that water onto the domestic hot water storage. But if it is not enough, then you go to the hotter tank, which in this case would be tank number 1. So it allows you. So our understanding is that it would help in that sense, is that you could actually have preheat. The problem that we saw here is when you are in recirculation mode, then if you are forcing water through tank number 2 that's going to be cooler than the domestic storage, then you're going to be working against yourself, and you're going to be cooling it in tank 2 and then heating it in tank 1 anytime you're recirculating. So that was our issue with this scenario.
I think I agree with, again, to the extent that I
Sure.
comprehend the system, which is low, I agree with your conclusions.
Okay.
And I also just agree with your conclusions because you guys are really good at this, and I trust your intuition. I just do. You haven't said anything that alarms me. I'm alarmed at the original design. You haven't said anything that alarms me.
Well, I should note then, just for full disclosure, that this was on our watch that this design was implemented. So there is some culpability. I mean, we did try our damnedest. It was design build, so we were limited in what we could have them. We couldn't just say, hey, don't do this, do this. It was kind of like, we have issues with your design for this way. What's your plan to change it? And then they would just completely redesign the system. And then we'd say, hey, we have issues on your new design. What are you going to do about it? And then they'd redesign it, and things get missed in that way. But I guess the last thing, and then maybe we'll have to.
Brian, I'm back, so I'm glad you guys are doing this. I appreciate it, but I'll chime in as needed.
Okay. How much have you heard?
I just got in. I heard David was alarmed by the old design, and I heard your point about the recirculation is the issue if we do it with that option. That was their option 2?
Yes.
Okay.
Okay. So you didn't hear me bad-mouthing you for
allowing this to happen.
For this happening on really our watch. Okay,
I
so that's
hear
good.
that.
Oh, okay.
I wanted actually to defend you on that because if you remember their initial design, you did the system diagram untangling, and you said, hey, don't you need a balancing valve here? Don't you need secondary pump? And they're like, oh, yeah. And then instead of just doing that, they redesigned the whole thing completely.
So the problem there, like what keeps me up at night, Jay, is that in hindsight, if I wouldn't have said anything, that initial system was so bad that the system just wouldn't have worked, and they would have had to fix it. So instead, by pointing that out, they made a system that just kind of works. It just doesn't work well, and it's a lot more subtle, and you've had to make this fight. So I feel even more guilty because of that, I guess.
Just out of curiosity, though, could you go back real quick to scenario 1 and your issue with this one?
So first of all, and I don't know if Gwen's sitting with you, but does this look correct to you for how because they proposed, they're not working off this diagram yet. That's kind of the first fight, I think, is to say this is a better way to represent the system, we think. and here's why.
Yeah.
So I think this is what they're showing on their revised M807. Would you agree with that, Jay, or is that?
I haven't spent enough time looking at it. The thing that I don't see on this one is the solar.
Yeah, so the solar, so each loop I have it changed. So this is how it is now, my understanding, and then this red is the change. And then
In scenario 1?
in both scenarios, and in both scenarios, the change from the heating hot water loop is from this to this, and those are meant to be caps where it just kind of stubs off there.
Yeah.
So the only scenario difference from 1 to 2 is that I see, and I think Gwen said this too, is on the domestic hot water side. So I think this is the scenario 1 that I wrote up was not preferred, and I don't know if you heard. Did you hear what we were saying to David about this?
No.
So my understanding, and we still got to field verify all this, and this is just initial, like, this is just my brain vomit, from what we have to work with. But the concern I have here is that it doesn't buy you much, because if let's say tank number 2 becomes the preheat or the lower temperature tank, so we can salvage more from the solar collectors. There's really 2 scenarios where you're going to need to be heating the domestic hot water. Either you have hot water, or the showers are in use, and you have a peak load and you have a lot of cold water coming in, but you're not going to get a lot out of this tank if it's at 70 or 90 degrees or whatever it would be, from taking a little bit of solar load. You're going to have to defer, I would think, to this tank more anyways. So this valve is going to be cracked more or completely, and this one's going to not be able to contribute as much. In the other case, where you're recirculating from the domestic hot water storage with these pumps 5 and 6, I think they are down here, then you definitely can't use this tank if it's at a lower temperature, because you want to keep this storage, it sounds like, at 140. Maybe you're letting it coast, but it's still going to be close to 140. And you're going to have to use the tank, the storage tank that's kept at 150. So if you happen to have solar load, I guess, that's gotten this to 150, which from the data that you sent doesn't seem like that's happening a lot. The way you have it.
We don't have any way to know that. We know the solar water can get up to 150 regularly. We just don't know how well it would work. How much it would heat the strat tank up.
Yes.
If there wasn't a boiler.
So from
heating
your
it up already.
Yeah. So I mean, you sent me data where you had the boilers locked out and the solar loop was getting up to 160, but your strat tank temperature sensor, where it was in the tank, which I think it was the higher temp sensor, was not getting up to 160 or whatever its set point was. That was closer to like sitting at 120, 130 when it was locked out, if I'm remembering that right. But that's a big caveat, is to say, yes, if you can get enough load out of the solar to get it up to those temperatures, then this scenario may have more value. But that's my concern, that I think is what needs to get communicated to, or what I'd recommend.
I share that. I don't think there's been, at least in my mind, there's never been an intention to only use the solar to heat up the strat tank enough to then heat up the domestic tank. It's really more been an idea of saying, can we preheat and then send that domestic water?
Yeah,
and
and
through the.
But I think the key here is that this doesn't preheat. It just gives you an option to bleed off.
Right.
Some amount, and what I'm positing, or what my theory is that you're gonna have very little time when you can use the lower temperature tank when it is at a lower temperature, and that's a big concern. So there's probably tests now that you have these isolation valves that you can do to validate or invalidate those suspicions, but right now that to me is the concern that makes it less preferred or suspicious, at least. And then this is scenario 2. So the last thing, and then I think I promised we'd go out to lunch on this side pretty soon. So I think maybe the thing to wrap up with, Jay, is this scenario 3 question mark that I put in that might be worth asking them about. And this is the one, David, that I'd be most interested in your reaction, because this is just my kind of wild ass theory that if you're going to do anything like what they're trying to do, it might be better to have a diverting valve at this first tee upstream of the strat tanks on the domestic hot water loop, so that instead of always having to go through the lower temperature tank, or what will a lot of times be a lower temperature tank, the preheat tank, you can decide to bypass that altogether and use the higher temperature tank that the boiler will be supplying, and will be, can be kept at 150 or even higher, if we have the solar load for it. But here at least you are putting them in series. You just have the option to bypass the lower temperature tank if you know it's not going to do you any good. There's some pressure concerns that Chris and I were talking about yesterday,
Yes.
that these pumps may not be sized, that we need to look at the Lochinvar pressure drop here. I mean, I know it's not like a plate and frame heat exchanger, so I don't imagine it's going to be gargantuan pressure drops, but it is, I think it's safe to say the pumps weren't designed to do this in series. They may be able to, but that's one of the things that needs to get figured out. So I'll stop there and see if you have any cautions or thoughts on that.
That, again, to the extent I understand the system, makes some sense. But here's what I just realized I think something that plays into this that may not have been considered, that I've seen be an issue before. And it's complicated. Like, the tank circulation pumps and the domestic hot water recirculation pumps are essentially in parallel with each other. Basically, they both kind of reference the storage tank, and they both kind of, come together at a T. And then compounding that problem is the GFX pump is in this weird sort of in series but in parallel also. And so where I'm heading with that is these pumps could be highly interactive with each other, and they have different heads, and depending on how flat or steep their curves are, the other thing that could really happen is you could reposition valves and stuff like that and not get what you wanted to have happen just because of the interaction of the pumps. And I think that might be true on the other side of the system too. So that right now concerns me, I guess. The limiting condition I've seen on the domestic hot water system twice, where a tank that basically was to charge the storage tank essentially was in parallel with the recirculation pumps, and one pump could deadhead the other pump, and you'd have these weird things happen out in the system. And they weren't in parallel because they were in parallel in totally different mechanical rooms. There's actually a case study about that in the pump troubleshooting design brief. So anyway, I'll shut up. But that I agree conceptually with what you said, but my overriding concern probably right now is the interaction of the pumps until I figured out I wasn't worried about that. And maybe you've already thought about that, or they've already thought about that, but that's like sort of where my head's gone.
I don't think so. I mean, that was one of the things that we pushed for when this was in commissioning, and I was back out there looking at it. Jay and I were pushing for functional performance tests that assessed for pump interactions, and we could not get somebody to pursue that. But that was on our list. I mean, that's always been a concern for us. Is that some of these pumps don't have balancing infrastructure associated with them, to even try to mitigate some of that. I don't think anybody's looked or thought about that. So I guess maybe to put that in a positive or next step, is there anything that we can do with this system diagram on the screen to better communicate that these pumps are, some of them are in parallel, some of them are in series, some of them are both to some degree?
Yeah, like I think just my gut sort of like if you shove the stratified tanks over to get rid of that double sort of L thing, the double whoop-de-doo, and I think you could untangle it another step that would make that clearer. And then like maybe the GFX pump, you actually end up rotating so it's sort of pointing. The GFX pump, I think when you do that, will kind of, not exactly, it'll end up in series with the first two pumps and the second two pumps, and then the domestic hot water recirc pumps and the tank circulation pumps. It's in a pipe between the two of them, and then, but it's also got the ability to pressurize essentially the domestic hot water storage tank, and the circulation pumps and the recirc pumps end up kind of in parallel with all that. I think, so I guess to answer your question, my temptation is to try and get rid of the double whoop-de-doo there somehow. That's what I'd start messing with in the system diagram, which gets into slide size issues, but like when I do these, sort of the last thing I worry about is fitting them on the slide. I draw them as untangled as I can get them, and then I deal with that with match lines and scaling and stuff like that. But I think that's what I've been sitting here wanting to do that in my head. Looking at this and listening to you talk, I'm thinking, I wish I could.
Yeah, no, I think that's doable. I think we could keep this slide. So Jay, if you're still on the, I think the way Gwen had it, where you know, as you look across the loops, the storage strat tanks kind of give you that common reference that they kind of stay in the middle of the page. I like that. I can make an additional slide that untangles this last one, and puts all the pumps oriented in the same way, and puts the strat tanks without having that bypass that kind of U-turns like that.
Yeah.
Yeah, and I also I rotate the GFX pump 90 degrees, and I put it up on the same plane as the recirc pumps, so it looks like the water, you know, if it really did go that way, it's going in series with that pump and then drops down to the other pumps or something. That's sort of where my head's heading with this thing.
Okay, and I'll probably start wasting all our times if I play with this too much, but you're talking about something like here?
But it's rotated the other way. And this is one of those things that's easy to draw but hard to express in words. So rotate that 180 degrees.
So even though it goes down that way?
Don't. Rotate it 90 degrees from that. Okay, now move that up.
Okay.
And put it downstream of the domestic water recirculation pumps. You're going to run out of space.
Oh, I see it right here.
Yeah, he wants it there.
Yeah.
Okay,
and
I got
now
it.
Now connect, that or else up in the middle or something. And then, you need to get the discharge of that. You have to shove the two tank circulation pumps and tanks over to get the double whoop-de-doo straightened out.
Yep. I can picture that. I'll if you're interested, I mean, this will come up on the class, so it is a cool one to, and your feedback is just knowing where your alarms are. It helps with my and our alarms. So I'll make that change today, and then I'll put this on the Google Drive, and we'll try to keep tracking this so that if we have a team call with this or session call next month, we'll continue to kind of clean this up and document those kind of changes and conversations. But yeah, that I guess last question is that it sounds like you're more worried about the pump interactions than you are about adding these tanks in series and what that may mean for these pumps' capacities to add that additional pressure drop of the valve and a second tank.
Not more worried. I wouldn't say I'm more worried. I'd say I'm equally worried.
Okay.
I think the pump thing may affect what you decided about, the interaction with the tank, because the pressure drop through the tank is a function of flow, and so if the pumps are interacting and varying the pump flow, that means the tank pressure drop is going to vary. And so I think understanding how the pumps interact becomes really important to all of this, I think. That's
Okay.
my gut reaction.
Yeah, so it's really all the same problem of
Yeah.
pump interactions and operating points on their curves, given all these interactions and configuration changes.
Right, and there's
Okay.
there's quasi decoupling bypasses, but not exactly. It's complicated. It's really complicated.
Yeah.
What about this, Dave? Is there a way that instead of trying to modify this,
I'm
would
really
it help to say
I get
what
really
what should we have gotten from the very beginning?
Something I said.
Well, actually, I was sitting here thinking that it'd be interesting to make a list of what are we trying to do here. We're trying to use solar energy. We're trying to recover water, recover heat from wastewater, and
Right.
I
Do you
think
wanna
we're trying to
go to lunch? Do you want to go to lunch?
basically have boilers that'll run as condensing boilers, but also supplement all of that.
This is a lot.
And trim it up.
It's fun.
Or
I think it was a great
cover
call.
the base if the other things aren't available. So make that list, and then
So I'm ready
figure
for lunch
out
and/or
a design that would do that. Like, there's this part of me that would love trying to do that. It would just be a matter of figuring out the time and how
I
I'd
think you're better at this than I am.
say I justify doing it, I guess.
It's hard to lean towards what we're looking for.
You've got to.
And I guess if you're really interested, I do have like that
get
stack of money
interaction,
sitting
so,
there
yeah,
from
I mean, I got some thoughts on
Leavenworth
that,
that we
I
are
think
just
it
sort of
went-
saying we'll use that for something.
People were
If you thought there was
participating, so
merit
I
for
think
me
it went
looking
well.
at this as a designer with a clean sheet of paper,
And we had the right questions. I mean,
I think that
I know
could
we
be
have
an
a few
interesting
more,
thing to
but
do.
time was also
I
running against us. We
definitely
wanted to get
think
to
a
the
lot of
answers.
times I've done that.
Yeah,
Like,
quickly.
this is so freaking confusing.
what'd you
Let's
think?
figure out what it should look like and just see how we, now that we got a working system on paper, how can we make this thing that we have match that? That really could be a valid approach.
You got your
You
phone
probably
recording?
are not going to be able to talk them into
Is that a
doing
lot
that.
of work to match the two up? Or since they start at the same time, is it pretty?
At some point, you may just have to say, fine, we own the system,
Until Prashant
thanks,
starts on
and
like
then
his
fix it.
project stuff, for stuff that we like the IGTP
Or get as
that we haven't
much,
started
get
on.
as
and
much
the
out
fall
as we
detection.
can at least.
I'm struggling
if
to
this
give
is
him
partial solutions.
tasks. So if that
I mean, the other
is
note is
something-
that the GFX
You could
pump, I don't even think it's ever
If it's more
run.
work to explain to him how to do it, don't worry about it.
because I
But
don't
if
think
if
the
it's something he can
control
help with
points
on this call
are
and future calls,
actually
he can help with that.
hooked up correctly to turn the thing on. Just so I'm understanding what your comment about the pressures of the pumps and where one could dead with the other. Could you give an example of that, of where you might see an issue, a potential issue?
Why don't I send you the design brief that has that case study in it?
Okay.
And it isn't this exactly, but it's basically, that's why I'm, in a way, it's this, a variation on that theme. But I think if you understood the case study and the design brief, then we could transfer that knowledge and apply it to this system diagram.
Okay. The thing that confuses me about this is those domestic hot water recirculation pumps. The water comes out of the pumps and it hits that first tee, and then it goes either up or down. If it goes down, it helps or it pushes the tank circulation pumps. But if it goes up, it fights against it. So you're adding pressure to both sides of that system. Do they cancel each other out?
I think it depends on a whole bunch of things. That you've hit the nail on the head in terms of, wow, this is really complicated, what could happen here. If you think about each of those T's as being a node that conservation of mass and energy has to apply to, and then realize that the conservation of mass part is related to how the pumps interact on their curves, and then as the pump interactions vary, the mass flows vary, which changes the temperatures, which is the conservation of energy part. It's incredibly dynamically interactive. It's just like
a new building.
Wow. Wow.
For David to say that.
So to me, the whole your idea of forget this. How could we do what we wanted to do if we had a clean sheet of paper? There's a lot of merit to that.
Look like this.
I think, including you may discover that it's like there's some thermodynamic impossibility-ish thing going on there. Like you can't concurrently do some of this stuff with real equipment or something.
Well, one of the questions I
Because you have to have approaches.
Hey, Jay, I just gotta warn you, we gotta hop off here in a few minutes.
Okay.
Can I ask one? I was just gonna ask one more question for you, I guess for everybody, but one of the things to ask about too, just in following up on your blank sheet of paper kind of idea, I know that the GFX units were really meant to be kind of a trial, like, hey, does this work, in this orientation? I know that for simplicity's sake, it's in a lot of ways it's easier to not worry about that as much as some of these other configuration changes, but maybe an idea to simplify it is to have them craft and have us help measure those pump interactions, specifically, involving the GFX circulation pump, and measure the heat exchange that you're getting from that. And if it's minimal, if it's really minimal, which I thought some initial data that you had made it seem like that, then maybe you just kind of decommission that system, and you've done.
I'm thinking the same thing.
Okay. And it's successful. You did it so you could try it, and you only did it on one wing, so you would know what it took to put them in, which was a lot, and you knew what it would get you, which we can look at. So that was my last thought, that this would be a good opportunity to get that and take out some of those pumps that are kind of making our head spin thinking through the dynamic interactions.